Our next speaker will be following through on what we've seen from Sir Joshua's presentation earlier. Now, I'm sure our audience here would be very interested to see a running ROS on a robot platform. And our second speaker, also from the DOST-ASTI, will be showing us a demo on the TurtleBot 3 ROS. This demo showcases the basic functionalities of ROS on a TurtleBot 3 waffle pie platform, specifically moving the robot via the Robotics remote control, moving the robot via RVIZ interactive markers, and simultaneous localization and mapping or SLAM. The basic ROS commands will also be discussed along with the user interfaces essential to the system. The next presenter is a Science Research Specialist 1, working on several electronics and hardware projects under the DOST-ASTI's Research and Development Division, or RDD. Some of her past and current engagements include the Smart Streetlight by designing and implementing a sensor board, and designing an online data collection dashboard on ThingsBoard. She was also involved in the programming of the DOST-ASTI's own biometric system, specifically the user interface and implementation of the hardware. She is also part of the AESS project and the AI Robot project, connecting and programming the sensors on the robot platform via ROS. Please welcome Ms. Marinel S. Sige.
Hi, I'm Nell, and for the second part of our presentation, I will be showing you a demo of running ROS on a hardware platform, specifically the TurtleBot 3. So TurtleBot is basically a ROS standard platform robot released by Robotics and comes in easy-to-assemble package. It is typically used for education, research, hobby, and product prototyping, and comes with a step-by-step guide on how to install and run ROS on a platform. So for this demonstration, we will be using a TurtleBot 3 waffle pie to showcase some of the basic ROS functionalities. To start off, we will open the terminal on the remote PC, aka the master. We will then run ROS core. This command sets up the ROS system and readies the master to send and receive commands. We will then remotely log into the robot via SSH. Once we've successfully entered the robot system, we will run this command. This launches the basic packages to start the TurtleBot. This basically sets up the publisher and the subscribers. We will then log into the robot again so that we can run the camera module. Once that's done, we will return to the remote PC and open the camera output of the robot. We will also launch another command that will send and receive data to and from the robot. So to see if the robot is now live, we will run RVIS. RVIS is a 3D visualization tool for ROS where we can see the status of the robot. Now that we have set up the robot, we can now control it with the remote control that came with the Robotics package. We can now change its position, and as you can see, the wheels in RVIS are turning. We can move the robot forward, backward, left, and right. And we can also change the speed of the robot by pressing multiple times on the selected buttons. Another way of controlling the turtlebot is through a feature in Orvis called interactive markers. To do this, we will simply run two additional commands to set up Orvis for control. Once the application loads, we can see the interactive markers around the robot. These are the blue and the red arrows. To move the robot around, we will simply drag the cursor to the position where we want the robot to move. To stop, we will simply double-click on the interactive markers. For the last part of the demo, I will show you one of the popular mapping techniques in ROS called SLAM, simultaneous localization and mapping. This is a technique where the robot draws a map of its current location as it goes around the area. For this demonstration, the robot will make a map of this room. To do that, we will stop all of the previous commands on the remote PC except for the ROS score and the camera output. We will then run the SLAM command and move the robot with the remote control. As you can see, the map is already forming thanks to the distance sensor installed on the platform. Let's just pan the map a bit and change its orientation. We will now move the robot around to form the map and cover the entire area. Now that the map is finished, we will then save it to our home directory using this command. Once that's done, we will navigate to the home directory and open the file. And it will now look like this. Comparing it to the real-life map, it's almost an accurate representation. The white section of the map represents the red tiles where the robot can freely move, while the black lines represent the outline of the map. This map can now be used for autonomous navigation, where we won't need to control the robot remotely. You can also learn more about the Turtlebot tree by visiting this website.